Let me start with something that's going to sound kinda insulting. Most people who study physics don't actually understand it. And I'm not saying they're not smart. Nah, not at all. I'm saying they did exactly what they were told to do. They memorized the laws, they memorized the formulas, they memorized the definitions, and they figured understanding would show up later, like interest on a bank account. Yeah, no, it doesn't work like that. You can know every major law of physics and still have no clue why the world behaves the way it does. You can write the equations perfectly and still stare at basic stuff like it's magic. Why hot things cool down, why stuff mixes and never unmixes, why time, for some reason, only goes one way. Here's the part nobody likes talking about. The fundamental laws of physics don't actually explain most of what you experience. They work just as well backward as forward. Run the equations in reverse, no problem. But try that in real life. A cup falls off the table and smashes to pieces. You're going to be waiting a real long time for it to jump back into your hand. Ink spreads through water. It never gets polite and pulls itself back together. If memorizing laws was enough, this would all be obvious. But it's not. So the real question ain't, what laws should you memorize? The real question is, where does understanding actually live, if it's not in the laws themselves? That's where we'll begin. Now here's where intuition usually goes wrong. Most people assume the world behaves a certain way because the laws force it to behave that way. They picture something deep inside the machinery of nature, some rule carved into the universe that says, things go forward, never backward. So you expect to find irreversibility written straight into the laws themselves. But when you actually look at the laws, that's not what you find. Take something simple, gravity. A planet goes around the sun in an ellipse. You film it, you run the film backward. Looks fine. The motion makes just as much sense in reverse as it does forward. Do the same thing with electricity and magnetism. Same deal. Run the movie backward, no alarms go off. Even down at the level of atoms, when two particles collide, the collision works perfectly well either way. If they can bounce apart like this, they can bounce apart like that. The equations don't care which direction time is pointing. So here's the problem. If the laws don't prefer a direction of time, why does everything else seem to? Why does friction stop motion but never restart it? Why does heat spread out but never clump back together? Why do you remember the past but not the future? If you were learning physics by memorization, this is exactly where you'd expect clarity, and exactly where you don't get it. Because knowing the laws gives you no warning this contradiction is coming. In fact, the laws quietly suggest the opposite, that the world should be reversible, and yet the world stubbornly refuses to cooperate. This is the first real lesson in how physics is actually understood. Understanding doesn't come from stacking laws on top of one another and hoping reality falls out at the bottom. It comes from noticing when the laws stay silent and asking why. The failure here isn't that the laws are wrong. The failure is assuming that laws, by themselves, explain experience. They don't. So let's take a case where everyone already knows the answer, but almost nobody actually understands it. Take a tank of water. On one side it's clear. On the other side you pour in some ink. For a moment the two are separated. Then you pull the barrier, and you wait. Slowly the ink spreads. The water turns this uniform bluish color. And it stays that way. Now here's the question that sounds foolish, but isn't. Why doesn't it ever go the other way? Why don't you come back later and find the ink politely gathered on one side again, leaving the other side crystal clear? If you're used to memorizing laws, you might think the answer is simple, because the laws forbid it, but they don't. Down at the level of atoms, nothing illegal is going on. The ink molecules and the water molecules are just jiggling around, colliding, bouncing off one another. Every single collision follows perfectly reversible laws. Run any one of those collisions backward, works just fine. So where did the one-way behavior come from? Here's what actually happens. You start in a very special condition. Most of the ink molecules are on one side. Most of the water molecules are on the other. As time goes on, random jiggling mixes them. That part's easy. There are enormously many ways for things to be mixed. But once they are mixed, the opposite process, unmixing, requires an astonishing coincidence. It would mean trillions upon trillions of molecules, all at once, just happening to wander back to their original sides. Nothing in physics forbids that. It's just fantastically unlikely. So unlikely you'd be waiting longer than the age of the universe. And this is where understanding starts to split from memorization. The laws tell you what motions are allowed. They do not tell you which outcomes dominate reality. If all you do is memorize laws, this example feels mysterious. But if you reason the way physics actually works, it suddenly feels inevitable. The ink didn't mix because it had to. It mixed because almost every possible future looks like mixing, and almost none look like separation. That distinction between what is possible and what is overwhelmingly likely, that's not something a formula is going to hand to you automatically. You got to learn to see it, and once you do, you start to understand why so much of physics behaves the way it does, without ever violating a single law. The laws tell you what's allowed, they do not tell you what's likely, and until you learn to see that difference, memorizing physics doesn't clear the confusion, it actually makes it sharper. So if irreversibility isn't hiding in the laws, then it's got to be hiding somewhere else. That's where we turn next. Now we can finally say what was really going on in that ink and water problem. The strange part was never that the ink mixed. The strange part was that the laws of physics didn't force it to. Every microscopic motion was allowed to go either way. And yet, when you step back and look at the whole situation, the system moves in one direction and not the other. So the first thing to learn, if you actually want to understand physics instead of just reciting it, is this. The laws of physics tell you what can happen. Understanding comes from knowing what almost always will happen. That difference, that's everything. When you start with an ordered situation, ink on one side, clear water on the other, random motion almost always destroys the order. Why? Because there are vastly more disordered arrangements than ordered ones. So as time goes on, the system naturally wanders into the bigger set of possibilities, and it stays there. This has nothing to do with forces pushing things in a preferred direction. It's got everything to do with numbers. If you could watch the molecules one by one, you'd never see a single irreversible collision. Every bounce would look perfectly reasonable in reverse. And yet, when you look at the movie as a whole, running it backward would look ridiculous. That's not because the laws break down. It's because the starting point was absurdly special. And this is why memorization misleads people. You can learn every law that governs molecular motion and still miss the point entirely. Because the point doesn't live at the level of single motions. It lives in the collective behavior of enormous numbers of them. And that leads to a deeper idea. When we say the world goes from order to disorder, we're not making a moral judgment. We're not saying disorder is ugly or sloppy. What we're saying is simpler and colder. Some arrangements are rare, most arrangements are not. The world doesn't remember the past because it wants to. It remembers the past because the past was more ordered than the present. Look at a partially mixed system and you can infer its history. If it's only halfway mixed now, it must have been more separated before. But the reverse inference never works. You never look at a well-mixed system and conclude it was probably even more mixed in the past. That asymmetry, our ability to infer the past but not the future, comes from the same source as irreversibility itself. And this is where physics stops being about equations and starts being about explanation. Real understanding means moving up and down between levels, from atoms to ink, from collisions to time, from laws to experience. The laws are necessary, they are not enough. If you learn physics as a list of rules, you never learn where those rules stop speaking. And the moment you recognize where the laws fall silent, you start hearing what the world itself is actually telling you. That realization changes how you approach every problem that comes next. Now let me show you a case that looks even more convincing and fools almost everyone the first time. Suppose I build a machine that only turns one way. a wheel with notches, a little pawl that drops into the teeth, a spring that holds it down. Try to turn it backward, it jams. Turn it forward, it clicks along happily. Looks irreversible. End of story. So here's the clever idea. Everything's being jiggled all the time by molecular motion. Air molecules are bouncing. Parts are vibrating. Hook that one-way wheel to a set of vanes sitting in a gas. Random motion keeps nudging it. Wrong way, it locks. Right way, it turns. Sounds like free energy. Perpetual motion, courtesy of clever design. But now you gotta stop admiring the trick and look close. For the pawl to fall into place, it has to lose energy. That means friction. Friction means heat. This part of the machine starts warming up. And here's the catch. As it warms up, the pawl itself starts jiggling. Eventually it jiggles so much it pops up as often as it stays down. When that happens, the wheel ain't one way anymore. It slips backward just as easy as forward. If one side's hotter than the other, the wheel turns, yeah, but only in the direction that lets heat flow from hot to cold. Flip the temperature difference and the wheel flips too. Once everything hits the same temperature, the motion stops. The machine never cared about clever design. It only cared about imbalance. Same lesson again, different costume. You cannot beat randomness at equilibrium. You can only exploit differences, and those differences always disappear. Now think about learning physics. People love clever shortcuts, memorized tricks, pattern matching formulas, procedures that only go one way. They look powerful until the problem changes just a little. Understanding works the opposite way. It survives change because it's built on why things fail, not on how they seem to work when everything's going right. Here's another way to see it. Imagine you're soaked and you grab a towel. It dries you. Great. Grab another towel. Still works. After a while, every towel's damp. Now no towel helps. You can rearrange them all you want. Nothing improves. The total amount of water didn't change. What changed was the availability of dryness. And that is what temperature really measures. Not how much energy something has, but how easy it is to move energy around. This is the part students miss when they memorize. Energy is conserved, yeah, but usefulness is not. Once everything's evenly spread out, the rules still hold, but nothing interesting happens anymore. That's not a failure of the laws, that's the consequence of them. So if you want to learn physics the way it actually works, you got to stop asking, what rule applies here? And start asking, what imbalance is being erased? That question will take you farther than any formula ever will. Now we can finally put all of this together. Look back at everything we've talked about. A pattern should be obvious. At no point did understanding come from memorizing a rule. It came from watching a situation fail in the way you expected it to work. The laws never told you why ink mixes. They never told you why heat spreads. They never told you why a clever machine can't cheat equilibrium. Those things only became clear when you stopped staring at the laws and started asking what actually happens when lots of simple motions pile up. This is how physics is really learned. You start with something concrete, something ordinary, something you think you already understand. Then you ask why the laws don't immediately explain it. That gap, that discomfort, that's where understanding lives. Feynman never treated equations as explanations. He treated them as constraints. They tell you what's allowed. They tell you what's impossible. But everything interesting happens in between. That's why he moved constantly up and down between levels, from atoms to towels, from collisions to memory, from temperature to time. He never stayed trapped in one layer, because no single layer tells the whole story. If you memorize formulas, you learn answers to questions you never asked. But if you learn how phenomena behave, you start inventing the right questions. And once you can do that, the equations stop being mysterious. They become bookkeeping tools, useful, precise, and limited. So the real method isn't study harder or practice more problems. It's learning to recognize what kind of explanation a situation demands. Sometimes the laws are enough. Most of the time, they aren't. And the moment you stop expecting laws to hand you intuition and start using them as guides instead of crutches, physics stops feeling like a collection of facts and starts feeling like a way of thinking that actually matches how the world behaves. There's one last point that's easy to miss, but it might be the most important of all. When you learn physics this way, by chasing understanding instead of memorization, you're not just learning how nature behaves. You're learning how explanations themselves work. Most of the things that matter in the real world don't sit neatly at the level of fundamental laws. Memory doesn't, history doesn't, life doesn't. Even time, as you actually experience it, doesn't. Those things live higher up, where lots of simple rules pile up into something complicated and one-sided. If you insist on staying only at the bottom, only with equations, you wind up confused about the very things you care about most. But if you stay only at the top, without the laws underneath, you lose precision, you lose discipline. Real understanding moves between levels. That's why physics, when it's learned properly, doesn't feel like a collection of facts. It feels like learning how to navigate a hierarchy of ideas, from atoms to heat, from heat to time, from time to memory, from memory to meaning. And this explains something else you might have noticed. The more you genuinely understand physics, the less mysterious it feels, and yet the more profound it becomes. Not because it gives you ultimate answers, but because it shows you how many layers sit between simple rules and lived experience. And this way of thinking doesn't stay in physics. It leaks outward. It changes how you evaluate explanations, how you spot fake understanding, how you tell the difference between something that sounds deep and something that actually connects. You stop asking, what rule do I apply? And you start asking, what kind of explanation does this situation demand? That habit is rare and it's valuable, because the world isn't organized to be easily summarized by laws. It's organized to be understood through connections, between scales, between ideas, between causes and consequences. Learning physics the way Feynman taught it isn't about sounding smart. It's about training yourself to see clearly where most people are satisfied to memorize. And once you learn to see that way, you don't just understand physics better, you understand the world more honestly.